Welcome to CEC lectures. Myself Dr. Preeti Jadwani from Department of Computer Science, Hyderabad College, University of Delhi. So moving forward in this series, we have started with the topic of string matching, and today it is the next lecture for string matching, in which we are trying to understand the string matching problem from the programming point of view, that how are we going to coin the details inside a program, and then we will be looking into a particular algorithm which is naive string matching algorithm. We will also be looking into a very valid exam or a particular example of this naive string matching algorithm, and we also try to analyze that algorithm in terms of complexity. So, this is going to be our today's agenda. Let us try to first understand the problem from a implementation point of view. Till this point we have understood that what is to be done inside this string matching algorithm. But now the next question which comes up is how it is to be done. Let us see. So, let us say we have given an array, assuming that array is named as T because we have named as at text. So, the name is T, and T is having the characters from 1 to n, that is the size of the T is n. So, n characters are there, and we also have a pattern array. That pattern array is to be looked for inside this T. So, that pattern array is named as P, and it is having the size of m characters. So, from 1 to m. So, T is from 1 to n, P is from 1 to n. Now, the problem, let us see the problem with a lens of the programming thing. The problem is to find an integer s which is called a valid shift, and this s will will be greater than equals to 0 and will be definitely less than n minus m, and we are looking for a valid shift in which our T, the characters T starting from T s plus 1 till s plus m, which is the length of the pattern, is going to be equals to P 1 to m. So, actually by this introducing the concept of valid shift, what I am trying to say here is this could be a shift of 0 characters if we are going to find our pattern at the first position, in which similar to the example which we have covered in our last lecture, the pattern was available at the 0th position and the 9th position. So, this 0, 9 and also the 12 are known as valid shift, in which we are going to find our pattern. That means, the characters of pattern P 1 to m will be equals to T s plus 1 to s plus m. So, S actually for the first occurrence where your pattern was available at the first position of the text, S is considered as 0, then 0 plus 1 is actually 1, and so on and so forth. So, we are going to find this valid shift, that how much your pattern is to be shifted in case of a if we considered as a sliding window. So, whether your pattern is matching with first 4 or first m characters, or if we are shifting it, then the next m characters, whether it is matching or something of that sort. That is what. So, basically we are looking for a valid shift here. In other words, we are simply trying to find out that are we able to look for, are we able to locate this P inside this the text T, that which means that P is a substring of T, yes or no, and if yes it is available, then you need to kind of report the location. And what are this P and T? Let me give you a quick recall that this P and T whatever the elements of P and T are there, they are the characters drawn from some finite alphabet. Now, that finite alphabet could be characters of any language, it could be 0 to 1, or it could be anything from bioinformatics thing. So, we have given a string T whose length is n. So, basically, so we have given a string T1 to n, the substrings are represented as Ti to j, and for some I which for some I and j where I is greater than equals to 0, I is less than equals to j and j is less than equals to n minus 1, the string formed by the characters in T from index I to index j inclusive. So, basically this process, in this process a substring could be a string of itself if we are going to take I is equals to 0 and j is equals to m. Then this then this process, a string is a substring of itself, then that means we have the string in which we are looking for and the substring which is being looked for, both as same, that is also a possibility. So, that we can say the proper substring of string T is string T1 to n is T1 to j for that same inequality in which 0 is less than I is less than equals to j and j is less than equals to n minus 1. So, we can have a proper substring of string S also, that is also a possible situation we can say. So, proper substrings if we talk about, so T I to j is equals to T I plus 1, T I plus 2 till T j for that equality. Now, why are we taking I greater than if I is going to be greater than j, then your T I j is equals to be an empty string which has a length 0. So, that means we need to be careful for the starting index as well as the ending index if we talk about the string things here. Now, various algorithms which we are going to study in our upcoming lectures about these about this particular task. So, we have 3 main algorithms. Again, the list is actually non-exhaustive and we have so much so many more algorithms for the similar task, but we are going to take these 3. One is naive string matching algorithm, another one is Rabin-Karp, and third one is Kunt-Morris-Pratt, which is more commonly known as KMP. If we look into the complexity, which is the time complexity and the space complexity of this, so that is given here in the table, but before that one more column is present in this table and which is known as pre-processing time. So, pre-processing time is something which is to be invested or which is kind of accounted before getting into actual algorithm, and that pre-processing time is actually once in one time which is to be invested or which is to be kind of spent only once for the whole algorithm or multiple runs of the algorithm. So, naive string matching algorithm, if we talk about, we do not have any pre-processing time because there is no pre-processing act involved, but in Rabin-Karp and in Kunt-Morris-Pratt algorithm we have pre-processing situations involved. Naive string matching algorithm, no pre-processing time, matching time, or we can simply say time complexity is theta n plus m, and the average is theta n plus m in average, otherwise it is order m and n. So, where m and n are the string lengths of your pattern and text. Space complexity or kind of the requirement of auxiliary space, it is not having any. So, for naive algorithm we have order m n complexity, no space complexity, or we can say just a constant space. We do not need any space extra apart from some counters to be maintained, and pre-processing is not to be done. So, no pre-processing time. Looking into Rabin-Karp algorithm, we involve some pre-processing act which is going to take theta m, and as far as matching time is concerned or the time complexity is concerned, on an average it is going to take theta n, and at worst it is going to take order mn. Space complexity is constant here, which is order 1. Then we have our algorithm Kunt-Morris-Brett KMP, in which the pre-processing time is theta m, the matching time is theta n, and the space which is kind of an or space complexity is also theta m. So, all these kinds of all the 3 algorithms we are going to explore at a detailed length. Let us begin with naive pattern searching algorithm. Naive, when we say, is actually, we can say it is the most simple or maybe the most obvious algorithm. So, that is why it is known as naive pattern searching. A naive pattern searching actually is a simple algorithm which is used to find all the occurrences of the pattern. Now, here also this is important, but whether we are looking for only the first occurrence of the pattern or we are looking for all the occurrences of the pattern. So, here it is going to report all the occurrences of a pattern, which is also known as substring within a text, and that text is also known as a string. So, we can say that we are looking for a substring within the string, or we can also say that we are looking for a pattern within a text. So, this algorithm compares the patterns with the text character by character. We will be taking an example soon, and moves one character at a time if a mismatch occurs. And so, the time complexity here is going to be order n multiplied by m, where n and m are the length of your text and length of the pattern. So, here we have text string with length m, pattern with length m, and the task is to print all the occurrences of pattern in the text, and without loss of generality you can say that n is greater than m. That means your length of the text string is always going to be greater than the length of the pattern. Now, let us take an example. So, we have a text which is known as, or which is having few words, and the text is, this is a test text as it is shown on the screen, and the pattern which we need to look for is test, and the pattern which is found when found, this test is actually found at index 10. You can count and verify. Here please count space as 1 character, because that is also a very valid character. So, this is having 4 characters, then 1 for space, then 2 for is, then again a space, then we have a, then again a space. So, the pattern is found at the index position 10. Then looking for some other kind of text which is not a normal kind of, we can say, English language test. We have A, B, A, C, and some such characters which are joined together to form a string, and the pattern which we are looking for is A, B, A, and this is the example which we have seen earlier also. Now, the pattern is found at index 0, the pattern is also found at index 9, and the pattern is also found at index 12. So, these are the 2 examples which shows us how are we, what is to be expected when we run or when we implement a naive string matching algorithm, which is there to find all the occurrences, or which is there to report all the occurrences of your occurrences of the pattern if they are available. Now, with the figure you can see we have a text, we have a pattern also. So, the pattern which is A, B, A, you can see now this is shown very clearly in the figure that your pattern is available at 0th position, then your pattern is also available starting from 9th position, which is 9, 10, 11 and 12, and your pattern is also available starting from 12th position, which is 12, 13, 14, 15. And now, here this 12th character which is A is actually, we can say here you can see on the screen, that it is shown in a dotted box. Now, what do you mean by this is shown in the dotted box? Some of the algorithms are going to utilize this information. So, we will be looking into this when we cover our KMP Kunt Morris Pratt algorithm. Now, the time complexity, if you can say, is order n square, or you can simply say it is order m cross n. So, it is it is definitely not a linear time algorithm. Auxiliary space, not much of the auxiliary space is required. So, we can name we can title it as a constant time auxiliary space requirement algorithm, which is order 1. And if we do the best case analysis, best case is order n when your pattern is found at very beginning of the text and you are looking for one occurrence, or we can say very early, that is order of n. Before this n going into the higher degrees, if we are having our pattern with availability of the pattern in the initial characters of the text or even at the first position, we will consider this as the best case, which is obviously order 1. So, the best case is order 1. Otherwise, if we look into the time complexity, that is kind of a quadratic complexity. You can name it as m cross n, or you can name it as n square. Both the ways it is going to be an quadratic time complexity algorithm with the auxiliary space requirement of order 1. Now, this algorithm, what actually it is going to do, that it will perform a constant number of comparisons, typically on the order of order n comparisons, where n is nothing but the length of pattern. How this is going to do, that we are going to look into the implementation part, but before going into the implementation part, we will first look into a kind of a full-fledged example through a complete dry run or through a complete run through, starting from the first position of the text to end of the text. Coming to the worst case complexity, as I told you, is order n square. So, when is this this worst case is going to occur? This worst case will definitely occur when your pattern does not appear in the text at all, or it appears only at the very end. Now, if you compare your best case and worst case of these pattern matching algorithm with your best case or worst case of linear search algorithm, you will find a kind of huge similarity. There also, if the element in case of linear searches, element is found at the first place, that is considered as the best case. Now, if element does not appear at all or appears at the very end, that is also considered as the worst case of the linear search. In linear search, we are looking for one particular element. Here we are looking for a complete pattern, maybe a a sequence of elements. Now, the algorithm, this string matching algorithm, will perform order of n minus m plus 1 multiplied by m comparison in case of worst case, where n you are aware that is the length of the text, m is the length of the pattern. So, total number of comparisons in case of worst case will be m multiplied by n minus m plus 1, because in the worst case, for each position in the text, the algorithm may need to compare the entire pattern against the text. So, take one position that kind of whole pattern is to be compared, and at last it is coming as no match, then because we are looking for the exact match. So, matching 3 characters out of 4 will not help us, we want a match of all the 4 characters. So, in this worst case, each position in the text, for each position in the text, the algorithm may need to compare the entire pattern against the text. So, let us say we have an example in which our text is 1 0, triple 1 0, then triple 1 0. That is our that is our text, and the pattern is triple 1, and the task is to find all the valid shifts. Now, what do we mean by all the valid shifts? That how much actually we want to shift our pattern if we actually want to align the text characters and the pattern characters. So, here I will be explaining this shift with the help of a pictorial diagram. So, here we have the text which was kind of written as the text here, as you can see, is 1 0, triple 1 0, triple 1 0. So, 1 0, triple 1 0, triple 1 0 is the text, and we have a pattern which is 1 1 1. And if we are trying to look for, so if in the first occurrence our shift is 0, because we have not shifted our pattern at all, we have just tried to align the text text 0 with our pattern 0. So, text 0, the element is 1, and the first element of the pattern is also 1. So, that is a match. So, if it is a match, we need not to kind of slide the pattern towards the right. We will be sliding the pattern towards the right in case of a mismatch. Now, we have found a match, then going to the next character. The next character of T, which is text, is 0, while the next character of the pattern is 1. Now, here is a mismatch. The first character of both text and pattern were matching, but not the second character. The second characters are 0 and 1 for text and pattern respectively. So, that means there is a mismatch. In case of a mismatch, we will be moving our pattern towards the right, and in the next part of the screen, if you can observe, it is written as S is equals to 1. So, S is equals to 1 indicates that we have shifted our pattern by one place, or the shift is 1. So, that is why S is equals to 1 is being written. Now, with S is equals to 1, we are comparing the second element of the text with the first element of the pattern, and then again here it is a mismatch of 0 and 1. So, in case of a mismatch, we will again be pushing our pattern onto the right side. That means we are again shifting our pattern to the right side. So, this is kind of a a sliding window which is moving one step ahead towards the right in case of every mismatch. Moving with shift is equals to 2. So, now we have 1 0, triple 1 0, triple 1 0 as the text which was there earlier. We have triple 1 as your we can say pattern. So, after S is equals to 2, we are, that means after shifting your pattern twice, we are actually comparing the third character of the text which is available at the second position starting from 0 if we talk about. So, T of 0 is kind of matched with P of 0. Now, here is a match, 1 is matching with 1 completely. Now, if there is a match, we are not going to shift the pattern. Instead, we will be kind of, we can say, incrementing the counter of your T and of your P, of your text, of your pattern both. So, one character is matched, then we try to match the second character. Second character is also getting match in kind of as both the characters are 1. Then with this matching, we will be moving. Now, again there is no mismatch for the two characters. We will not be kind of will not be shifting our pattern further. Instead of that, we are incrementing the counters, and we will be able to check your last character of the pattern with the fifth character of the text. Now, that is also matching. So, 1 1 1 starting from the position 2, 3 and 4 are perfectly matching with 1 1 1 of your pattern. So, we can say that S is equals to 2 is a valid shift. Now, S is equals to 2 is a valid shift. Let us try with S is equals to 3. So, when we say S is equals to 3, we are moving our pattern into the right direction. That means, now we will start comparing the first letter of the pattern with the fourth letter of the text. So, 1 and 1 are matching, again incrementing the counters, again 1 and 1 are matching. So, 2 characters are fine. But coming to the third character, which is 1 in case of the pattern, and in case of the text, if we are looking at the 6th character, the target is 4, 5 and 6th character. So, 6th character is 0 and the third character of S when matched, third character of pattern when matched with 0 is not going to give you a match. So, that means S is equals to 3 is not valid. So, again a mismatch. So, in case of mismatch, we will further push our pattern towards the right side. Now, we will be having S is equals to 4. So, in S is equals to 4, we have only one character matching. So, that one character is the first character of your pattern matching with the 5th character of the text, fine. Moving forward in terms of counters, now we have 0 and 1 which are certainly not matching. That means S is equals to 4 is not a valid shift. Push the pattern on the right side, start comparing the 6th character of the text with the first character of the pattern, 0 and 1 no match. Again start pushing. So, that means S is equals to 5 is not a valid shift. Then again start pushing your what we can say, pushing your pattern. Now, we have the 8th character, 9th character and the 10th character of your text matching perfectly with the first, second, third characters of the pattern, which are 1, 1 and 1. And if we if we are looking into the shift, so we have shifted 6 times. So, we can say S is equals to 6 is a valid shift, because in case of S is equals to 5, the first character was not matching. Then we moved it further. S is equals to shift is going to give us the whole match of all the 3 characters of the pattern. So, S is equals to 6 is also a valid shift. Now, in this naive string matching algorithm, we will be moving further our shift to S is equals to 7, and when we give it as S is equals to 7, we are at the last 3 characters of the text and we try to match them. The first 2 characters of the pattern are matching, but the last character of the text is 0 and the last character of pattern is 1. So, not matching. So, S is equals to 7 is not a valid shift, while S is equals to 6 was a valid shift. Now, after this, there is no point in moving your pattern forward, because we are not left with the characters, enough characters within the text to be matched here. So, text is left for only 2 characters and we have the pattern length as the 3 characters. So, we will not be moving further. So, in this way, using the concept of shift, we need to find the valid shifts where actually your text and pattern are going to be matched. Now, in this lecture, we closely looked into the naive string matching algorithm. We tried to understand the best case as well as the worst case of these. We looked into the complexity also, although we have not analyzed the complexity completely because we have not written the algorithm as of now, and we also tried to understand what is the concept of actually what is the actual concept of a valid shift and how are we going to use that in our naive string matching algorithm. More to be covered for our string matching algorithms in our upcoming lectures. I hope you have enjoyed this one. Here is a list of references which is being used for the preparation of lecture. I will see you in the next lecture. Till then, take care. Goodbye.